As the topics addressed in this workshop demonstrate, the problem of assured autonomy is huge, and there are many different aspects to solving this problem. So what I would like to talk about is one that we think is really fundamental to the problem of ensuring trust in autonomous systems, and that is the problem of measurement, in this case, measurement of coverage of the input space. That is, covering the combinations of input values and variables that really matter and that ensure that the system can work properly in all environments that are encountered. Now, the differences between assurance of conventional software and systems and autonomous systems was recognized early, and this is just some summary of the 2012 Defense Science Board study. This goes back 10 years ago. There was a very careful study looking at what it would be needed for assurance of autonomous systems. And I'd like to call your attention to just a few of these points that were brought out in this study. In particular, the parts underlined in red. The first is the difficulty of enumerating all conditions and the non-deterministic responses of the system. So as you can see, that is an issue that comes out very quickly in looking at autonomous systems. The systems have to respond to conditions that are encountered in the environment, and it's going to be very difficult, as we know from any software, to ensure that the system responds no matter what conditions are encountered. So that's especially critical for autonomous systems and machine learning for reasons that we'll get into in just a minute. And then the second consideration that's underlined here is the measurement of trust. How do we know that we've done enough testing? How do we know that the autonomous system has been trained sufficiently and with respect to the right inputs to know that it will respond no matter what inputs are encountered in the environment, and that it will perform as properly as expected by its human operators? So that's, again, another issue of this. So the measurement of trust is what we're concerned about. Just for background, let's take a look at some aspects of conventional software safety assurance and a couple of different domains. So for the first one, commercial software, and by this we mean things like apps that you might use for online commerce, ordering apps, maybe video games, that sort of thing. Typically, and this is just an average, but typically about half of the cost goes into code development and the other half into verification and testing. But as you might expect, systems that are life-critical, in particular, and almost uniquely, I could say, aviation life-critical, the situation is really very different. Now, this is from a NASA report looking at the use of the FAA-required safety assurance codes and standards for aviation software. And for life critical, about 12% of the cost goes into code development and nearly 90% into verification and testing. So that is an enormous problem, an enormous cost. And as noted also, software tends to be about 30% of the cost for a new civilian aircraft. So this is an enormous cost, and this is for basically conventional software. So a couple points here. One, it means that it's very expensive, but it also means that we know how to do conventional software and guarantee safety. But the problem is a little bit different for autonomous systems. When DARPA looked at this problem and set up a program to address it, it was recognized right away that the cost of traditional, conventional testing for autonomous systems would be just enormous and really prohibitive. As you can see, the quote here, it says that traditional testing would require about 11 billion miles, 500 years, at a cost of $6 billion, and so on. So this is an enormous cost for conventional software testing and assurance for autonomous systems. So therefore, DARPA made it clear that there needed to be a better way of doing this kind of assurance. So as pointed out a couple slides ago, we know how to do very high assurance, life-critical software for conventional systems, such as aviation. And it is expensive, but maybe we could use the same processes, maybe autonomous or AI systems could be used in assurance, maybe to speed things up or to make things less expensive. But the problem is really much harder than that. You can't just use the same approaches that you use on conventional software because a major part of that depends on structural coverage criteria. In this case, modified condition decision coverage, but basically that's you can think of it as a stronger form of branch coverage, looking at conditions within branches. But it's a white box structural coverage criterion, and it really is not useful, not practical to use for a lot of machine learning systems, on which, of course, autonomous systems really depend. Structural coverage, of course, refers to branch coverage, statement coverage, and that sort of thing that depends on the source code, looking at paths through the source code, branches that are covered within the source code, such as we see here. That's very effective for conventional software, which is deterministic, and we want to make sure that we have looked at all parts of the software. But it doesn't work so well for machine learning. The reason it doesn't work well for machine learning is that the machine learning systems generally run the same algorithms. So there's a machine learning algorithm, typically a neural net, or in many cases a neural net, where the inputs are used to train the system. The algorithm is the same. It uses the same algorithm every time, and the behavior of the system that is generated, the model that is output, the system that is used by the autonomous vehicle, for example, that depends on the way in which the system was trained, and that depends on the inputs that are used. Now, what it's looking at are the conditions, connections between the nodes, but producing those nodes is mechanical, and everything depends on the inputs used in training. There has been some useful research in looking at ways of measuring coverage for machine learning systems, typically neural networks, looking at what's called neuron coverage to ensure that different parts of the neural net have been trained and are used fully in producing the results. But at this point, it's not clear if this is going to be sufficient for assurance of the accuracy and correctness and safety of the output. So we really need to do more than that. And one of the things that we've been looking at is the idea of measuring the input space. Now, there are statistical measures of data coverage, and those are very useful. And we have extended those ideas looking at combinations of variable values, and we'll talk about those in just a minute. But the idea there is that if we look at the combinations of input values that are encountered in practice and ensure that the system can handle these combinations, then we've got a direct measure, a direct assurance that the system is working properly. Recall the Defense Science Board study where it said there is a real need to be able to cover combinations of inputs because that is what's so critical. I included this slide just for fun, but it does make an important point. So as shown here, it says scientists have trained rats to drive little cars around a board to collect their food. So it doesn't take a lot of intelligence to drive a car, clearly. But this is driving the car around a little board, a little maze, tabletop size, and they are very constrained. So the problem that we face for autonomous systems, of course, is that we need a very large range of inputs that can be handled, because there are not so many constraints in the real world, and almost anything can happen. So that's the real key challenge in assurance of autonomous systems, making sure that your system responds properly no matter what combinations of inputs it encounters. So no surprise here, as we all know, testing is really, really hard to do well for a complex environment. And these are a couple of examples of autonomous vehicle failures that led to accidents. I mean, serious accidents, in one case fatal. The first one, of course, a camera that didn't respond correctly when the autonomous vehicle encountered a white truck against a bright sky, and I think there was an angle involved there as well. Second one, failing to pick up street signs, lane markings due to the angle of the car, the rain conditions, and the direction of the sun. So 3 different combinations there. So here again, we're going back to that Defense Science Board study that said the problem is enumerating the conditions and the response of the system to those conditions. So we really need to understand combinations of conditions that are part of the testing and training of the system. So what I'd like to walk through right now is a relatively new approach to measuring the coverage of input space. And we think this applies very nicely to autonomous systems. And I'll give an example later of a first application of that. But there is a lot of value in this approach also to ensuring the coverage and the thoroughness of coverage of regular tests for conventional software. But it does apply to autonomous systems, in some ways even better, I think. To understand that, let's just walk through this little example. So here we have 4 tests. So each row represents a test. Here's one, all zeros, 0, 1, 1, 0. So 4 tests, 1, 2, 3, 4. And 4 different variables or parameters, A, B, C, and D. And these in this case are binary. They don't need to be, but in this case, to make things easier to show, they are. And what we're concerned about is the coverage of combinations of input variables. So A and B, if we take these 2 at a time, the first one could be A and B. We've covered 0, 0, we've covered 0, 1, and we've covered 1, 0. However, 1, 1 is not there, so we've covered 3 of the 4 possible settings of these 2 binary variables in this case. And then we go and take all the other pairs, all possible pairs. In this case, there's only 6 pairs, 4 choose 2, and then we start to consolidate those coverages. So if we look at B and C, only 2 settings are covered, 0, 0, and 1, 1. And here they're repeated. So we've covered half, or 50%, of the possible settings of B and C. However, for C and D, for example, we've covered everything, 0, 0, 0, 1, 1, 0, and 1, 1. Putting all that together in a table like this, we can look at the coverage of every single pair, and it looks like this, 75% for 3 of them, the lowest is 50%, and 2 of them are covered fully. Now, if we rearrange this table and put the rows in order of coverage, starting with full coverage, 100% coverage, then we generate a sort of simple step graph that looks like this. So everything under this curve, everything under this red curve represents conditions that are covered, which is clearly true because they came straight out of the table. The area above the curve represents combinations of input values that are not covered. Putting all this together, we can get a table that, or a graph that looks like this. So the area under the curve, again, represents the combinations that are covered. That's straight from this table right here. And the area above the curve represents incompleteness, or combinations of input values that are not covered. So the level of completeness is the area under this curve, which in this case is about 79%. These combinations over the total number of combinations, possible value combinations, which is 24. So we've covered 79% of the possible value combinations, and that of course means that 21% have not been covered, so we don't know what would happen up in this region here. What this means for assurance, of course, is that we know what the system will do for the combinations shown in green here. So this is that area under the curve where we have tested input combinations. However, the area above the curve, this is the region for which we don't know what the system will do. So even if we've got 100% branch coverage, even if we can apply this to conventional software, of course, even if we've got full branch coverage, we're not really sure what's going to happen if the system encounters a combination of values that is in this region right here. We don't know what will happen. And on an autonomous system, this is even more critical because everything depends on the input combinations that are used in training. So we need to be able to measure and identify this region right here. To demonstrate the utility of these ideas for measuring thoroughness of a test, we applied this to a large real-world example. Now I want to point out that this is not an autonomous system. These ideas were actually developed before we started applying them to autonomous systems. But this is spacecraft software, 82 variables. Most of them were Boolean variables, not all, and about 7,500 tests. And these were developed quite a few years ago using conventional test design, not specifically using combinatorial methods based entirely on expert knowledge and conventional test approaches. So it was an interesting case study to see if this level of testing, these large number of tests, 7,500 tests, maybe it covers combinations, but in reality it's pretty good, but it doesn't cover all combinations. What we show here in the red line, this is two-way combination coverage. So again, everything under the curve is covered. The area above the curve represents combinations that are not covered. So the area under this red line right here is about 96%. So that's very good two-way combination coverage. If we look at three-way combinations of input variables, we have something under this blue line, which is quite a bit less. And we extend this out, in this case, to four-way coverage. That's the area under the green line. And five-way coverage, the area of combinations of five variables. And that's under this orange line right here. So you can see that this is just a little above 50%. So the coverage of five-way combinations is not as thorough as we would like, and even the four-way combinations. This is a direct measure of the degree to which the input space has been covered. In this case, it was input space for testing, but we can also apply it to input space for training. So what we would like to do is apply these measures of input space coverage to machine learning data sets. In other words, the data sets used in training machine learning applications. So just to get a sort of a baseline, tried some of these out on some well-known samples from the Weka open source data mining tool, which has a number of different machine learning algorithms available. And these examples have pretty good results, but we wanted to measure the coverage. And just a quick summary, what we see here is that the two-way coverage, again, this is the red line here, is really not that great. So better than half, maybe two-thirds of the two-way combinations are covered by these samples that are used for learning the Weka data mining tool set. And even smaller proportions of the three-way combinations, that is the blue line, and so on. So that's kind of interesting that you can get pretty good results from machine learning even with an input space that is not especially well covered. But again, these are overall data accuracy rates. This is not looking at what would happen in a real world case where there is some really obscure condition that occurs. And that, of course, is where accidents tend to happen, or where the very, very unusual combinations of inputs suddenly appear. So there are a lot of interesting research questions that arise in looking at input space coverage. As we've seen on the previous slide, a lot of really good results can be obtained with relatively low combinatorial coverage. So that suggests that we might be able to improve results with better input space coverage. But it also means that there are probably a lot of corner cases that are being missed, and so we may be able to deal with that issue as well. Another consideration, looking at conventional software, we have lots of studies that show that a small number of factors are involved in all system failures, usually 1 to 6. Very, very rare to see 6 or more factors involved in system failures. So a natural question is whether this same situation occurs with autonomous systems. And that's something we don't know the answer to. That is very definitely a research question. So the other aspect is whether input space coverage and classification prediction problems can be handled using combinatorial methods to basically to do machine learning. We may be able to identify classes of inputs based on the combinations of values that we see. That's another interesting research question. And there's some more work that we really don't have time to touch on today, but looking at sequences of input value combinations, what we call sequence covering arrays. There may be some really useful applications of these to autonomous systems as well. For a practical application of these combinatorial coverage ideas, let's look at the issue of transfer learning. What this is the issue of moving a model from trained in one environment to a different environment. As the model is trained, there are always going to be some differences between the training data sets, the test data, and then finally when it gets to the real world. And if we apply the same model in a new environment, there may even be additional differences. So there's a key question, a very practical question that occurs in the field of machine learning, which is how do we predict performance of a model that's been trained on one data set and it's applied to a different data set. It may be only slight differences, but typically when you move to a new environment, you may have more variation among the elements that are being looked at. There may be different values, different conditions that can arise, and so on. So we need to be able to ensure that a model trained on one environment will work well if it's exposed to a somewhat different environment. The typical way of handling this problem has been to do random testing, looking at randomized inputs, and just trying to make sure that the random inputs cover the new environment well. And the idea is to ensure that there's at least one of every object type, values, and so on. However, these practices don't typically ensure that interactions are being covered. Combinations of input values, which, as we've shown, are really important. So what we're talking about today could be used to ensure better coverage of interactions among input values. So here's an example of the transfer learning problem. This is based on data sets contained in Kaggle, and the problem is to identify if an image contains or does not contain an airplane. Seems fairly simple, but it's not so easy looking at these aerial images. So there are two data sets, one from Southern California with 21,000 images, and another from Northern California with about 11,000 images. 12 different features, and these are discretized into 3 different bins by pre-processing. So the transfer learning problem here is to train the model on one data set and then see how it works when applied to the second data set. So what was done was the model was trained on the larger data set, the Southern California data images, and then applied to the smaller data set. And also the model was trained on the smaller data set and then applied to the larger data. And the results seem somewhat backwards. The model trained on the large data lost performance when applied to the smaller data set, about half the number of instances, whereas the model trained on the small data set, when applied to the large data set, there was no decrease in performance. So that seems like you wouldn't expect that, right? Because if you have a larger set of data, you would expect better training. But it turns out that that is not the case, and the reason is because of the interactions in the two. And here's the explanation for why the training on the smaller data set worked better than training on the larger data set. The reason is that there's a greater density of combination variability in the smaller data set. So when applied to the other one, it had already seen and was trained to do the correct response for just about any combination it saw. As with any research area, at this point, early in the research, we have a lot more questions than answers. But we have some good leads. It looks like, based on what we've done so far, that combinatorial coverage is of value. So here's a few speculations on where we might go next. The first consideration, interactions of larger components with other programmed components, and also where humans are replaced or are humans involved. So it might be that the failures look more like human factors issues. We don't know that. Maybe we could have a Turing test for bugs. Did this bug arise because it was a trained machine learning system that wasn't trained properly, or was it a human? Lots of different questions. Really, the system failure, the nature of system failures is very different with these new systems. Let's just review the key points one more time. So the first consideration is that autonomous system components are becoming very commonplace, used in many, many different areas, and that's going to be a normal state of practice from now on. And the really important point is that the methods that are used today for conventional systems really don't apply well to a lot of autonomous system components. Looking at structural coverage is not really that useful. Formal proofs are good, and they can prove properties of the algorithms, but they have their limits as well. All of these practices have limits. The key here is to identify how to put together a good set of assurance practices. Another consideration, dealing with learning systems that change their behavior as they learn. That's even harder. And so overall, we really need to develop much better measures of test adequacy, and we're arguing that looking at the combinatorial coverage of the input space can be really useful in this regard. And here's contact information, also project website. We have a lot of papers there published over many years, including our work and some others. So feel free to contact me or my colleagues at any time if you find this useful. And thank you.